Okay, so today we're going to be talking about the second derivative and the things that we can do with it. In order to do that, though, we first need to start by reviewing what we've talked about uh, for the first derivative. So for the first derivative, we have done a few things. The first thing we did was find critical points. The second thing we did was to determine whether those critical points were extreme values or local extrema, and that's going to be our local max or our local min. Okay. And then after that, we determined the intervals of increase or decrease. And to do those things, I mean, you can do any one of them. As a matter of fact, you can do all of them basically at the same time by following a few steps. The first step is to take the derivative. The second step is to set that derivative equal to 0. The third step is to solve for x. And the fourth step is to take those values, those x values, and put them on a horizontal line test. And then once you put those values on a horizontal line test, you can tell if the critical points are maxes or mins or neither. You can determine all of your intervals, whether the function is increasing or decreasing, and you'll know where the x value is for those things. But if you want the y value, which questions don't always ask you for, as a matter of fact, they usually don't. But if you want those y values, you can do this fifth step, and that is to plug your x values into your original function f of x. And then once you plug it into your original function, you solve it out, and it'll give you your y value. Okay. Now for the second derivative, we're going to do basically the exact same process, but we're going to do the same process to figure out something different. Okay. So the terms here are really important. We have inflection points. And inflection points are places where the second derivative changes sign. Okay. Places where the second derivative changes sign. That means it goes from positive to negative or negative to positive. And then the next thing, instead of intervals of increase and decrease, or however you want to call it, we're going to be finding intervals or places where the function is concave up or concave down. A question might ask you to describe the concavity of the function. Okay. So for determining whether it's concave up or concave down, it's hard to define those things, or to define it. It's hard to define those things with words. It's easier to do it with an image. Concave down just means it's a downward facing curve, and concave up means it's an upward facing curve. That's it. So when you are trying to figure out where your inflection points are and your intervals where a function might be concave up or concave down, we're going to do a few steps. The steps might look familiar. First step, take the second derivative. The second step, set it equal to 0. The third step, solve for x. The fourth step, horizontal line test. And the fifth step, if they ask you for the y values, is to plug x back into the original function, f of x. Okay, and that's it. Those are your 5 steps. Notice they're the exact same steps except for step 1, which is to take the second derivative. And that should be everything you need to know. I'm going to do an example problem to, show how this would go. So we'll take a graph like f of x, or a function like f of x is equal to x cubed minus 2x squared plus 4x minus 1. Sure. We're going to take the derivative of that. It's going to be 3x squared minus 4x plus 4. And then we're going to take the second derivative of that. So we could use the first derivative and find our critical points and our intervals of increase and decrease and maxes and mins and all that fun stuff. We're going to skip over that and jump straight to the second derivative, which is going to be 6x minus 4. And then we're going to set that equal to 0. We're going to solve for x. Simplify it if you want. And then we're going to put that x value, there's only one solution, so we only have one thing to test, on a horizontal line test. So where the inflection point is going to be at x equals 2 over 3. Okay. Although to be technical, we don't know if that's an inflection point yet. Remember, an inflection point only occurs where the second derivative changes sign. So if we end up with something like this, then it turns out that x equals 2/3 wasn't an inflection point all along. So just like you can have a critical point that's not a max or a min, in the second derivative, you can have a place where the second derivative is 0, but it's not technically an inflection point. Okay. So let's test some values, test something left of 2/3, make your life easy, use 0 when you can, and use 1 when you can. And we're going to plug this in to the second derivative, okay? So I like to put a little note on my horizontal line test that tells me whether I'm looking at the first derivative line test or the second derivative line test. So this is the second derivative line test. So we're going to plug 2/3 or 4/6 into the second derivative. If you plug in a 0, you're going to get -4. So this is negative. And if you plug in a 1, you're going to get 6 minus 4, which is 2. Okay. So that, 2 is positive. So that means that we did have an inflection point. So if we're looking at intervals, from -infinity to 2/3, we are concave down. Anytime the derivative is negative, the second derivative is negative, you're concave down. Anytime the second derivative is positive, you're concave up. So that's 2/3 to infinity. We are concave up. And there you go. So where's the inflection point? Well, the inflection point is at x equals 2 over 3. And if you wanted to know the concavity, you would put that it's concave down on the interval -infinity to 2/3, and it's concave up on the interval 2/3 to infinity. And this is how you would solve this type of a problem.